So the work energy theorem, this is what relates work and energy. Energy, we said, is the ability to do work. Aiden, how do we find work? Work equals what times what? This was limited because you couldn't have a changing force. You had to have a constant force. The force and the distance had to be in the same direction. It was okay. Work was also the area if you had a force versus distance graph. Work was that area. We'll look at that more in Physics 12. I'm not going to be harping on that as much here. But the best definition of work, you know what? It's on your green sheet, probably right underneath the law of conservation of energy. I think it even says the work energy theorem, W equals. It's the change in stored energy plus the change in kinetic energy. Oh, once again, what's change in anything? Also on the top left corner of your formula sheet. So it's PE final minus PE initial plus KE final minus KE initial. But you know I'm not going to write all that out when I can abbreviate. Where do we use it? Well, example 1 says this. A cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. So I'm just going to make a little note here. What's the total mass we're talking about? 65 plus 7.2, 72.2 kilograms. If she's pedaling over level ground, underline the phrase level ground. You'll see why. Okay. Emma R., what's it asking me to find? How much what? You're back. I caught you zoning. What? Yeah. Don't write this down. Here's what my brain would think. My first thought would be, well, work equals force times distance. And I would say, oh, to increase her speed from rest to 5 meters per second. That's how much work. Do you see a force in newtons, Emma? Do you see a distance in meters? No. My second thought is work is also the area under a force versus distance graph. Be stupid obvious. Did they give me a graph? Now I would move to the work energy theorem. I would say work equals the change in potential plus the change in kinetic. And then I would ask, are any of these zeros? What 2 words did I underline? If you're on level ground, are you gaining gravitational potential energy? Are you losing gravitational potential energy? So we can say that this is 0, and the reason we can say that it's 0 is because we're on level ground. If there was a hill, though, I could work it in, so this also still works great for roller coasters. Is there some kinetic energy in this question? Are we moving? Okay, let's expand that. Change in kinetic energy. Massimo, what's change in anything? Okay, so I can write this as the work is going to be the KE final minus the KE initial. Oh, Massimo, why can I do that? Yay. So you'll notice I can find how much work was done, how much energy was poured into this system without a force or a distance. Instead, it's going to be a half mv final squared. It's going to be 0.5 times 72.2 times 5. Don't forget the squared. How much energy did this cyclist lose from their body so that they could get their whole system up to 5 meters per second? Because the energy came from somewhere. The bike and rider gained kinetic energy. It came from the sugar that the person had eaten, the food energy. What'd you get? Emma, what'd you get? Yep, you're typing, I know. 902 even? Let's go 902.5 because I'm going to be using this for a reason. Is that correct, folks? Joules, because it's work. So pause. First, when do I use the work energy theorem? When they say how much work, but I don't see a force or a distance or a graph. Then there's probably going to be a change in. B, Emma F. What's B want me to find? Still work, but now what? To increase her speed from? Okay, it's going to be the same procedure. We're going to write it out once. It's going to be change in potential plus change in kinetic. Are we still on level ground? So we can say, okay, that's 0. What's change in anything? I'm going to do 2 steps at once. I'm going to say, okay, so you're saying it's a half mv final squared minus a half mv initial squared. Oh, masses don't cancel. I know there's an m in both of these terms, but there is no m in work, so masses don't cancel. Are any of these 0? Not this time. So I'll just have to crunch it. Okay, I can do that. Work is going to be 0.5, 72.2 times 10 squared minus 0.5, 72.2 times 5 squared. What do you get? $2707.5? This is interesting to me because Emma F., how much did we increase our speed by in part B? And Emma R., how much would we increase our speed by in part A? But we don't get the same answer. Why? How come? This is where that squared I told you really dominates your life. And one of the ways it dominates your life is once you're moving fast, it takes even more energy to go faster, even by a little bit. In fact, let's do another 5 meter per second increase here. So it's going to be the same idea. Is it okay? I'm not going to write all of this steps out. I'm going to say, I'm pretty sure because we're on level ground, it's going to be a half mv final squared minus a half mv initial squared. The work is going to be 0.5 times 72.2 times 15 squared minus 0.5 times 72.2 times 10 squared. To go up by another 5 meters per second. Don't forget your squareds. Thea, let me know what you get. Sorry? 4512.5. Is that right, folks? Yeah, an even bigger increase than before. This right here, for example, this is why if you look at rockets, when you see a rocket that's being launched into orbit, 80% of it is fuel. Because we got to get rockets going really fast. That squared really kicks in. We need a lot of energy. We got to carry it with us, unfortunately. It's just mostly fuel. Oh, speaking of rockets. Example 2. A model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Okay. Well, let's be a little bit obvious here. Cade, what are they asking me to find? Good, you're back with me? I'm going to come at you. My first thought, Cade, don't write this down. I would think, well, work equals force times distance. I don't see a force. Now, I see a height, and so I might be tempted to go mgh. But what else do you see in this question? A speed. You know what? I think this is going to be the work energy theorem. So instead of force times distance, I'm going to say it's the change in potential plus the change in kinetic, or the change in kinetic plus the change in potential. I can't remember what order I wrote it on your formula sheet. Is there a change in height in this question? So I can't cross this one out. It's not level ground like the previous question. Is there also going to be a change in speed? You know what? Let's expand these. What's change in anything? Good. So I can say this. Work equals PE final minus PE initial, and then plus KE final minus KE initial. There's my final minus initial and my final minus initial. Are any of these zero? Gravitational potential energy is zero when we're on the ground. Are we ever on the ground? Aiden's nodding. Where? Oh, yeah, launch, right? Kinetic energy is going to be zero when we're at rest. Are we ever at rest? Yeah, we're going to be at rest at the, well, actually, it's going to be right here. And it sounds why, because before we hit launch, how much energy, is it moving yet? No. So we're actually going to hit a top speed of 85 meters per second. Okay. Cade, what's the equation for gravitational potential energy? Gravitational potential energy. PE. It's right next to the 1/2 one. 3 letters. Yeah. And then plus, hey, what's the equation for kinetic energy? Yep. Do the M's cancel? Sebastian, is there an M in work? No. And of course, yeah, it should take more rocket fuel to put a bigger rocket up. The M shouldn't cancel. So it's going to be 0.5. No, not 0.5. That's the second one. M 0.15. G 9.8. 340. That's how much energy you need to get from the rocket engine to get to the right height. But also 0.5 times 0.15 times 85 squared. That's how much energy the rocket engine needs to contribute to get to the correct speed. If you're wondering why I keep referring to rockets, Philip, in Physics 12, this is what we'll use to calculate how much fuel to put a rocket in orbit. It's kind of the rocket equation. Cade, what'd you get? I have no idea. 1,041 point. Is that right, folks? Yeah, I'll go 1,042. That's 4 sig figs. That's pretty good. And I don't see a part B. So we're not going to keep all the sig figs. I like example 3. 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 Example 3 is a nice question. Example 3 is a nice question. I underlined level ground. A car is traveling at 35 meters per second over level ground. Leo, what's this question asking me to find, Leo? Keep reading. The word stop is also going to be a word I need to notice, so I'll underline it just to say, make sure you pay attention. Okay, don't write this down. Leo, my first thought would be, well, work equals force times distance. Do you see a force here in newtons? Do you see a distance here? Work is also the area under a force versus distance graph. Be stupid obvious. Do you see a graph? So we go to our third, it's our most cumbersome definition of work, the work energy theorem. It's the change in potential plus the change in kinetic. But, ooh, this is nice. Are we over level ground? Are we over level ground? Are we over level ground? So let's try that again. Are we over level ground? Say yes. That's nice because that means my change in gravitational potential energy is zero. I didn't gain or lose any height, so that never changed. That's why I can say that. What's changing anything? So this is going to end up being work equals KE final minus KE initial. Oh, are any of these zero? Comes to or bring it to Oh, so one of these kinetic energies is zero. Which one, initial or final? Yep. Yep. Well done. So I get this. Work equals negative 0.5 mv initial squared. Negative 0.5 times 1250 times 35 squared. What'd you get? This should be a fairly big number, but negative, because this car has to lose a lot of energy to come to a stop. Leah, what'd you get? Negative 765625. Is that correct? 765625. Now, what's the negative telling me? This car has to lose energy to come to a stop. Ah, okay. B. Jacob, what's B want me to find? Force. What did I find in part A? There isn't by chance a version of work that has force in it, is there? Work equals force times distance. Get the F by itself. Okay. By the way, I also said, what's creating the force? What force brings cars to stop? And it also is the same force that makes them go forwards. Yeah, if I wanted to, I could say this is the force of friction, which means I can go negative 765,625 all over 82, answer button divided by 82. What do you get? 9,000. I'm going to go 9,340 newtons. Now, it's negative. What's the negative telling me? It's telling me that the force is in the opposite direction of the distance. I would be fine if you left the negative off. I would take a positive or a negative answer here because I really didn't say what direction. I just kind of wanted the magnitude. Oh, okay. Justin, what's C want me to find? No. Coefficient of friction. How do I know it doesn't want me to find friction? Because I think that's what I found in part B, the force of friction. Oh, what's the equation that has a coefficient of friction in it? We said friction was mu times the normal force, and this is asking me to find the coefficient of friction. Yeah. Well, let's get the mu by itself. How would I move the Fn over? So I'm going to get this. Mu is equal to the force of friction divided by the normal force. I don't know the normal force, but I think if I imagine my free body diagram, I think in this case, the normal force is just going to be mg. And here, this is going to be my answer button. So I'm going to end up with answer button divided by, what was the mass? 1250. What was G? 9.8. What kind of a coefficient of friction between the tires and the road do we need to make this work? .76, which is pretty high. Is that right, folks? If you were a road engineer and you ran these calculations and you got that, you would say, okay, we need to change the speed limit on this corner or on this road. It's like if you're coming to a stop for a stop sign, or we need to put a warning stop sign further ahead so that people have more time, more distance to stop. Because this one, you're only stopping on a hot summer day with this kind of coefficient of friction. If it's raining, this usually drops to about 0.3. You're plowing through the stop sign and hitting something. Example 4. I don't know if you remember, but near the beginning of the year, we looked at an RCMP question where I had the cell phone pick up the sound of the skids. And I said, in real life, that would never happen. That would be such a fluke that the cell phone voicemail picked up the sounds of the skids. And so we knew how much time it was skidding for. I said, we're going to come back to that question when you have more physics. Here it is. So Lyndon, I like this question. I like this question. I like this question. An RCMP officer is investigating an accident. A car has struck a pedestrian at a school crosswalk. There are no witnesses, no cell phone recordings, nothing. The officer measures the coefficient of friction at the accident site to be 0.65. They have an instrument that they use that can measure that. And he measures skid marks that are 49 meters long. Should the RCMP press charges against the driver? What do you think we need to find here in order to figure out whether the RCMP should press charges? Which velocity? Initial, because what's the final velocity of every car accident ever? Okay, so I'm going to say this wants us to find VI. And here's how we're going to solve this. We're going to start out by writing something stupid obvious. I'm going to say to you, work equals work. Don't argue with me. I know that's right. What was our first definition of work? The one that just had something times something. Now, how do I know to go with that? I do see a distance. So on the left-hand side, I'm going to write force times distance. On the right-hand side, I'm going to say, okay, I'm going to use the work-energy theorem, the change in potential plus the change in kinetic. Keaton, looking at this question, the way it's described, is there a hill at all in this question? No. If there was, by the way, you can work it in. I'm giving you one on level ground so that we can say this is 0, but it's not that much more difficult if there's a hill. You measure the height of the hill and you have MGH final goes right there, and you can still crunch the numbers. Okay, and what's changing anything? We're going to get this. Force times distance equals KE final minus KE initial. Massimo, which one did you say was 0? So now do one more thing. Look up. You can put a negative right there if you want, because the force and the distance are in opposite directions. The car is moving forwards, but friction is pointing backwards. What I want you to realize is this negative and this negative are going to cancel. What we're really going to end up with is this. Force times distance equals, and then you can either write 0.5 mv squared or mv squared over 2. Most of you have told me you prefer this one. So, okay. Hey, Massimo, get the v by itself. Divide the m and also divide the 0.5. That's going to give me a v squared. Yeah, you want to find the initial speed? It's going to be the force times the distance divided by 0.5 m square root. Which force Yeah. Problem. Do I know the force of friction? Justin, friction is what times what? I don't know the normal force, but you know, if I imagine my free body diagram, I'm pretty sure that this here is mg. So friction is going to be mu mg. I could crunch that, but notice what happens when I walk over here. If I put it in, I get mu mg, there's the d, divided by 0.5 m. Anybody notice anything? Jacob, what? The RCMP doesn't even need to know the make of the car or the mass of the car, and they can still determine the speed. All they would need to know is what type of tires, and they would probably just use an average tire mu first, and then once they discovered the car, they would redo the calculations with the correct coefficient of friction. But what's kind of nice here is, yeah, the mass of the car cancels. What's mu? I don't know what's mu with you. Philip, what's mu? What was the skid distance? Or sorry, G, 9.8. What was the skid distance? Sorry? How fast was this car going minimum? Because it might have slowed down before skidding. And I told you I like this question, I like this question, I like this question. I also like it because, first, I'm fulfilling a promise I made to you. But notice, it contains work and energy. It contains a little kinematics. It contains a little forces. We'll put a little friction. It's kind of almost everything we've done this year, aside from momentum, in one. 0.65 times 9.8 times 49 divided by 0.5 square root. Y'all get 25? Could you multiply that by 3.6? What's that in kilometers per hour? 90 in a school zone? Yeah, we can charge this person. Yeah, dumb people and speed. Put your pencils down, look up. This was posted stupidly on YouTube a few years ago. On Vancouver Island, a guy with a motorcycle decided he was going to post a dash cam video, but it wasn't a dash cam, it was a fuel tank video of him going really, really fast. And this gives us some nice numbers because we can see the speedometer in the video. Come on, working on it. I like that I can see the speedometer. Why are we looking at the sky right now? Okay, this guy's not, anyway, not a safe driver. How fast are we going? Kilometers per hour? Look closely at the black inner numbers. Look at the outer numbers. The inner numbers are kilometers per hour. This is miles per hour. So, time for a unit conversion. Siri, convert 220 miles per hour to meters per second. 98.35. You know what? We'll call it 100 meters per second because it's pretty close. Okay. By the way, you're covering a football field every second. Do you think you can possibly react to that? Okay. He slowed down to 100 miles per hour. Here's the question I want to ask. I'm curious how much energy was transferred to heat during the slowdown. And just because I'm a nerd, I'd like to know how many light bulbs we could light with that energy. To do that, we're going to need some numbers. So VI was 100 meters per second. VF, convert 100 miles per hour to meters per second. 44.7. So let me go like this. Let's get back to here. So first of all, VI was, what was it, 100 meters per second. VF equals 44.7 meters per second. A is asking how much energy is lost as the motorcycle slows. I think what that's going to be is the change in kinetic energy. The track looked pretty level to me. Yes, I didn't see a hill. So I think what I'm really saying is this. I want to find out how much work the brakes did. That's going to be the change in potential plus the change in kinetic. I'm going to find the work done by the brakes. Raghav, no hill. I didn't see one, so we can say this. What's change in anything? So it's going to end up being a half mv final squared minus a half mv initial squared. It's going to be 0.5. Did I give you the mass in the question? Yeah, I did a Google search. The rough mass of the motorcycle and rider is about 300 kilograms. So 300, and then V final is 44.7. Don't forget the squared. Minus 0.5, 300 times 100 squared. In case you're wondering, yes, the RCMP traced the YouTube channel, figured out what idiot had posted this, and confiscated the motorcycle. Yes. What do you get? How much energy? By the way, it's going to be big. Yeah, I saw Aiden. Huh? Read me all the digits. 1, 1, 2, 0, 0, 2, 8, 6, 5 joules of energy. Although we get a negative answer. Why? Because we're focusing on the motorcycle. It lost energy. Oh, okay. Let's try this again. Read me the digits. Okay. Does that energy just, is that right? Cade's still typing. That's okay. Yeah, you got the same thing? Does that energy just vanish? No, it's got to go somewhere. That's where the law of conservation of energy GG says. So B asks, where do you think that energy went? I'm looking for a word that starts with letter H, baby. Heating up the brakes, heating up. That was wasted as heat and sound, but primarily heat. C says, how many watts of power were generated in stopping? Ooh, we haven't done power for a few days. Resa, power, what's the power equation? On your formula sheet. Power is work over time. I got the work. I'm going to chuck the negative. It's 1200286.5 5. We need the time. Can you all get your smartphones out? Open a stopwatch app. I've backed the video up to when he's doing 200 miles per hour. Right when you hear him start to slow down, you'll hear the engine whine change, hit start, and then right when we hit 100, I'll say stop. Oh, here we go. Start. Stop. What was your time? So, let's go 16.3-ish. How many watts of power? So answer button divided by 16.3. I missed a number. I missed the square, Mr. Dueck. I'm trying to do this myself because I can't remember the answer. I just know it was big. I'm ignoring the negative. 6. I'll go 73,600 watts. Yes, power's measured in watt. How many 60-watt light bulbs could this light up? Divide by 60. How many light bulbs could you power? Sorry, how many? This is why with both hybrids and electric vehicles, that regenerative braking system is so nice. Instead of that energy getting wasted as heat, a big chunk of that goes back into recharging the batteries. Very clever. I'm going to skip that one. So, questions that I think you want to practice for the quiz. 1 is good. 2 is good. 3 is good. You can skip 4. You can skip 5. I'm skipping the graphy questions. You can skip 6. You can skip 7. You can skip 8. You can skip 9. Hey, Mr. Dueck, you can skip 10. You mean Mr. Dueck is just 1, 2, and 3? Those are good practice, and I'll have a study guide for you on Monday. I'm reading the room. A lot of you still are working on lesson 1, 2, 3, 4, 5, and 6. If you want the study guide ahead of time, you can wait till Monday. Give me 1 second.